So first and foremost, for any hypothesis testing, what we do, we state the null and alternate hypothesis. So first step is state the null and alternate hypothesis. Okay, first of all, state clearly what is the null hypothesis, what is the alternate hypothesis. Okay, then step number two. Step number two is select a relevant statistical test for the test statistic. So depending upon your task, you will choose whether what kind of test statistic are you going to implement here. For example, if your sample is less than 30, then you can go for student's t-test or t-test simply. If you have greater than or equal to 30 samples and you know the population standard deviation, then you can go for z-test. Okay, so the second test is select a relevant statistical test that is relevant for your use case. Select a relevant statistical test. There are a lot of statistical tests. Out of them, what makes sense in your case? F test. Then there is whatever you mentioned there. All this goodness of it. chi-square test, F test, etc., etc. Okay, just think. The third step is derive the distribution of the test statistic. Okay, under null hypothesis. So assuming that the null hypothesis is true, we derive the test statistic value. So derive the distribution. Derive the distribution of test statistic. We call it test statistic under null hypothesis, assuming that null hypothesis is true. For example, for normal distribution, okay, normal distribution which is z-test, we will with the z-test with known mu and sigma, so that will be the distribution of that. If we are using for the for a sample which is a normally distributed sample, then we can use the z-test statistic, and with a known mu and sigma, I will get the distribution of it. So the distribution will be like this. Okay, so that's the third step. Then the fourth step is select a significance level. Okay, so I'll talk about this. Select a significance level. This term also, what is the maximum acceptable false positive rate. Max acceptable false positive rate. Generally, okay, denoted by alpha is equal to, generally it's 5%, also 1%, and for medical it is even less, 0.1%. I'll discuss about that. Medical test it's even less. So generally 5% is the norm. That's the alpha, a significance level. If it is beyond that, then I'll accept the null hypothesis, that I am willing to accept 5% false positive rate. If you don't understand false positive, I'll discuss about that also in this video only. Now compute the p-value. The fifth step is compute the p-value. I'll discuss about what is the p-value also. All the terms will be clear. Compute the p-value from observed whatever. Once you have the distribution, okay, you have the distribution of the test statistic. From that, whatever is the value for under the null hypothesis, okay, you will compute the p-value from observed value of test statistic. Okay, that is generally we write it as t observed. T is for the test statistic, OBS is for the observed. So we'll compute the p-value, and then finally on the basis of this, decide to either accept or reject your null hypothesis. And 6 is accept or reject null hypothesis based on whatever is the significance level that you have seen. Based on alpha. Alpha is your significance level. Alpha, p-value, these are important terms. Okay. These are your 6 steps. Okay, we'll come back and revisit it again one by one. Let's understand it using an example. Okay, let's do. So let me state a question for you so that you understand better. So the question is that we have to do the hypothesis testing to compare the mean recovery time of 2 drugs or 2 medicines. Okay, we have to say I have one medicine which treats some condition. So I have to compare the which drug is better. So I have to compare the recovery time, and we'll use the mean of the recovery time as our metric to compare the two set of medicines. And each medicine is tested on some set of patients, some number of patients, and there are two groups, and now we have to compare these two. So we don't know which is better. So now based on the data that we have, we will see that how to formulate. So today we'll not solve the problem exactly, but this is to explain you the framework. And when we go into exact tests, t-test, z-test or chi-square test, then you will solve exact problems. But this will be too much for you. So today I'll just explain you the concept using broadly, or meant to explain the framework to you. So the question is, do the hypothesis testing, HT, to compare recovery time, recovery time of two medicines. So you have to do this, medicines. There's a medicine 1, medicine 2, and we have some data. So for example, the data is in the format that you have patient ID, then whether medicine 1 or medicine 2 was given, and then there was recovery time in days. For example, patient ID 1, medicine 1 was given, and recovery time was like 7 days. 2, medicine 2 was given, recovery time was like 8 days. 3, and so on, like that. You have some sample. This is the data you have, sorry. This is the data you have. And based on this, now you have to tell which medicine recovery time is better. So that's the hypothesis testing you have to do. Okay. So we need some metric to compare these two medicine, two groups. So here we'll choose so out of this, first of all, we choose that we'll go with the mean to compare. If the mean recovery time of medicine 1 is less, or mean recovery time of medicine 2 is less, whichever is less, that is better. That's what we can compare. So we'll choose mean as the metric. So we'll choose mean recovery time. Okay, and let's denote it for the two mean recovery time as mean recovery time for medicine 1 and mean recovery time for medicine 2, like that, MM1, MM2. Okay. So this is the setup. We have to compare now which one. So depending upon what we have, so we will find out which is better, and depending upon the thing that we want to find out, that tests will vary. The alternate hypothesis will change. The hypothesis will change. Null hypothesis always remains the same, that both are same. Nothing is changed, status quo. Both the medicines are same, everything is equal. So that will be my null hypothesis. So there are two things that we can use here. So we can use t-test, as I mentioned earlier. So first thing is, what are the choice of tests we can use? So state the null and alternate hypothesis. Okay. So first of all, let me test. So null hypothesis, I will say that both medicines have the same recovery time. So my same recovery time means medicine M1 recovery time, mean recovery time of medicine 1 is equal to mean recovery time of medicine 2. This is my null hypothesis, that everything is same, nothing changes. And my alternate hypothesis is, this is my step 1. Now depending upon later on when we go for 1 and 2 tail test, right? So depending upon what is my alternate hypothesis, the type of test, the way we are measuring it will vary a little, because everything is a distribution. So we'll see which tail to look at. But let's go with the simple one first. So alternate hypothesis is that no, both are not same, and I'm claiming that my mean recovery time of medicine 1 is less than mean recovery time of medicine 2. That's what is my claim. It can also be the other way around, that it is not, or it can be like both are not equal, just this one. But for this, we'll go with this 2 for first. Let's easier to understand. Not equal to is even more complicated. Okay, so my null hypothesis is that both the medicines are same, nothing has changed, everything is equal. And my alternate hypothesis is that no, mean recovery time of medicine 1 is less than mean recovery time of medicine 2. Means medicine 1 is better. This is my alternate hypothesis. So we'll go and verify this. If it is valid, we'll accept it. Okay, if we find it, or else if we don't find this is true, then we reject it, and automatically this will become true. So this is my alternate hypothesis for this case. And what are the tests? So second, this is step 1. Step 2, select a relevant statistical test. Relevant statistical test, so what are the choices that we have? Step 2, relevant statistical tests. So I have two options here. For example, either I can use t-test, student's t-test, in case the number of samples is less than 30. Generally in medicines, we have because we cannot go and conduct medicine test on thousands and thousands of people, right? Even they do it, but generally when statistics came into play, the sample size was very small. Okay, when these tests were invented, student's t-test. So generally n less than 30 is what we can expect in medicinal trials. So n is less than 30 plus population standard deviation is not known. Population standard deviation, that is sigma, is unknown because for such a small population we don't know anything. Or we can use the z test. These are the options 1 and 2. That n is greater than or equal to 30 means the sample is large and my sigma is known. Okay, so depending upon these, so I'll check. Okay, so when I look at the sample data, I will know which condition is it meeting. Say for our case, I am going with the t-test and the number of samples is less than 30 and the standard deviation of the population is not known. So I'll go with the t-test. So I have chosen this. Okay, so I choose t-test and this I'll continue throughout the example. Okay, so step 3 is, what is the step 3? Let's see. So derive a distribution of the test statistic under null hypothesis. So first of all, I should know what is the test statistic. Okay, so the test statistic would be, first of all, all these tests have a test statistic. So let's see what is the test statistic here. So for t-test, and here we are comparing two means, right? So it is a 2 sample mean t-test. Okay, that's what we are doing. We are comparing two samples, mean of one with another mean. So we are doing this. So what will be the test statistic for this? So let me see. So if I am not mistaken, we'll see this again in the test t distribution. But for now, let's see that this is my this is for same variance. And remember, same variance. Okay, let's not go into the details when I discuss student distribution, then I'll say. But let's see, I'll give you the test observation. This is my test statistic. Okay, so my mean 1 and mean 2 comparison, it compares to mean and then we standardize it so that the test becomes standard. Standardize it with the divide it with its means, s1 square by n1 plus s2 square by n2. Let me write it for you. What is this? So mm1 is the mean, sample mean of m1 and n2, sample mean recovery time, whatever is the recovery time. S is the sample standard deviation and n1 is equal to sample size. Okay, so this is how you do a two sample mean test. So you have two means, you just do a subtraction, you can take the subtraction of them and then you can just standardize it by dividing them with this is a standardized standard deviation. Okay, so we have standardized it. So this is s1 square is the variance, right? The square root of that is standard deviation. So if you divide, both are same units. So for example, if this is in days, mean recovery time, so even this will be in days, this will be day square, and finally this will be in days, so days by days this will become unitless. Okay, so this is your test statistic. Now this is clear. So if the two means are very close, what happens if the two means are very close? If they are very close, this is saying null hypothesis that if both are very close, my t observed will become 0. It will be close to 0. If both are very close, and then this will be close to 0. For example, if this is the kind of distribution, assume even t distribution is symmetrical, but its tail is a bit different. Okay, and say this is your mean. Okay, if both the means are different. This is your distribution of the test, this t observed. This is the distribution of t, this test statistic. That is this distribution. This is the PDF. Of t test or t distribution, sorry. So it also has degree of freedom, etc. I'll not discuss that now. That is there in the other video. So it is the PDF of t distribution and this is mu. So if both are very close, that is my null hypothesis. Both are almost same. There is no difference between them. So it will automatically come near 0, right? And if both are not same and there is a vast difference, they will go away from 0. So for example, if mm1 is less than mm2 otherwise, so it will go this way or this way, it will go away from the mean. I hope that is clear. Okay, so keep this intuition in mind. We'll use it later when we understand how to accept or reject it, and when we understand p-value and critical value, etc. Okay, so this is your step 3, that I have now a test statistic with a known distribution. So I have the distribution for it. Derive the distribution of the test statistic. My test statistic for the t-test 2 sample mean t-test is this. This is the test statistic. I have all the values. From the sample I can compute, right? I have the sample. From this I can, all these data. From this I can compute the mean. For M1, for M2, I will have the standard deviation for both the values. For M1 and M2. And N1 and N2 is the sample size. I have all these values. I can calculate the t observed from this. Simply. Okay. And then I'll see. And I know that this is a t distribution. I can go and find out the t distribution for the given data. And from there, I'll find out where is t observed on this. Whether both are equal, then this will be close to 0, or whether there is a lot of difference and they are close to the tail somewhere here. This t observed is coming here somewhere, or here somewhere, depending upon the alternate hypothesis, whatever we have. So where it is lying on this, and depending upon that, we'll do further analysis. I hope step 3 is clear. This is very important to understand. Now, what is my step 4? Select a significance level. Max acceptable for false positive rate. Generally that is 5%. So let's select it as 5% only. So my step 4 is select some alpha, and I'll select alpha is equal to 5%. This is my significance level. Generally this is selected. 5% is my tolerance level. What is my step 5? Okay, what is step 5? Step 5 is compute the p-value from observed value of t statistics. What is p-value? Okay, understand this. So let me draw the, so whatever I've drawn this, and let me draw it again. So say for example, this is the t distribution. Okay, this t distribution is also symmetric. This is the t distribution, and now I have to, you get the, say for example, if you get the t observed somewhere here, the value that I calculated, this is your t observed, this one t observed, you get it somewhere, this is your t observed. Okay, so the, what will be my p value? So my p value is equal to probability of seeing any value t which is greater than or equal to t observed. So this is a PDF. This is a PDF of t distribution. So what is the probability of seeing any value which is greater than or equal to t observed? If I want to find it from the PDF, the complete PDF is, this complete area is 1. Right? If I want to compute anything which is greater than mean, so I'll move here towards the right, the area under the curve. So that's what will give me. PDF area under the curve gives me the probability, right? In the PDF. So here, how will I find the probability of observing something greater than or equal to t observed? If I find the area under the curve which is here, right? If I find the area under the curve which is there, this area under the curve, that is the probability. This is my p value, the probability value, the area under the curve which is greater than or equal to t observed. Okay, I hope this is clear. So let me shade it for you. So this is your p value. Okay, the area under the curve. The area under the curve gives me the probability, right? So this is the probability of observing something greater than or equal to any t which is greater than or equal to t observed, this and beyond. I hope p value is clear. Okay, and say for example this area under the curve comes out to be, so either there are only two possibilities, either it can be less than 5% or greater than 5%, and also we have to find out whether this 5% step lies, right? 5% is the area under the curve, right? This 5%, this complete is 100%. Is area equal to 1? PDF area is 1, right? So where will be the 5% line lie, so that the area beyond this is 5%? Say for example in this case, let's point it. Say for example this is that point, that is alpha, and this is, say this is t alpha, and this area is equal to 5%. The significance level, it says that at least 5% of the area under the curve should be at least 5%. The total is 100%. So this is your t alpha. Now think, my significance level is that at least 5% false positive I can accept. Okay, max, not at least, max 5% I can accept here. Okay, so what it says, that if it was here or it is greater than this, my significance level, okay, then I can accept my null hypothesis. Means, say for example this is your mu. So understand, this is the difference between them. They should be very zero. It should be zero ideally under the null hypothesis. But I'm saying, oh, even if it's not zero, till here, if it is here, okay, if it is till here, then I'll accept it. But if it goes beyond this, till here, the complete area under the curve is 95%. This is the region. For example, let me color it with the different color. Let me color it with orange. This is the remaining area. So if it is in this region, this orange one, it should be ideally close to zero. Both the means should be same. That is my null hypothesis. But even if it is still here, so that my 95% of the area is covered and the remaining 5% is not covered. Okay, so this is my significance level, that okay, 95% of the area also it falls, no problem. Okay, and this 5%, if it is more than this, then I will accept it. So this will be your acceptance region. We call it acceptance region. So beyond this t alpha has got a name. Okay, this t alpha is called critical value. Critical value. So this is the test statistic beyond which my area would be equal to the significance level in this, that is 5%. And if my observed comes 5% or more, okay, 5% or more, this because this area is 5%. If you go this side, this will be greater than 5%. This area, so it will be beyond 5%. So it comes in the acceptance region. We accept it. But if you go beyond this, the t observed, if this moves this side, this will go less than 5%. So now this has become, so say for example this is t observed is less than 5. Say for example this is only 3%. My p value is only 3%. Okay, so this is less than your t alpha, less than the critical value. So I'm willing to accept something that is like till 95% if I'm getting. But if it goes beyond this, I'm not going to accept it. So if it is falling, my t observed is falling in this alpha or this region, my t observed is falling anywhere here. Okay, anywhere here. So I will accept it. But if it goes beyond this, the area under the curve will become less than 5%. So my p value will be less than alpha, and I will reject the null hypothesis. Here this is 3%, and I wanted that at least 5% should be there. That's my significance level. At least this much should be there. Okay, so this blue region will be called, I have a name, this is called rejection region. Means if my T observed goes beyond T alpha, then I'll reject it. If it is less than T alpha, I'll accept it. And this T alpha, the area of the curve beyond which it is 5%, that is my critical value, and the P value is beyond which my T observed, the area under the curve is there. I hope this is clear now. So here, what is my P value? My P value is equal to 3%, which is less than P alpha, which is less than alpha. That is my significance level, alpha equal to 5% or significance level. We have computed this now. And these values generally we have charts as we have log tables, right? So we have tables. So we have z-score or t table for other chi-square test table. Also we have test tables like we have for log. For which value we check that table and find out for each value, because it's difficult to compute. So they are ready-made tables, and from the table we'll see the value, what is the value that is there, and depending upon that we'll get the value. And if my T observed goes beyond that, in this case, then if it is greater than, because it is 0 is here, it is going greater than this, so I'll write it as 0 so that you don't get confused. This is 0. So the area under the curve becomes less and less, and now I cannot accept it. This has gone in the rejection region. So I will, in the step 6, what is my step 6? Accept or reject null hypothesis based on alpha. So here, as I have explained so much, my null hypothesis will be rejected. So I reject null hypothesis. If I reject null hypothesis, means automatically I accept alternate hypothesis. That means that mm1 is less than mm2, whatever is the hypothesis. This is just for understanding. Okay, so I'm just showing that whether how to accept or reject. I hope these 6 steps are clear. Okay, so we discussed about critical value, beyond which the area under the curve will be equal to significance level, and if my T observed is towards the, in this case, towards the right of it, then automatically the area under the curve will be less than significance level, then I will reject it. If my T observed was here somewhere, for example, if my T observed was here, then the area under the curve will become greater than 5%. If it is here, say for example, this becomes 7% or maybe 10%, right? Then automatically this is greater than, my P value will become greater than alpha, right? This will become greater than alpha, P value. Then I accept the null hypothesis. So if my T observed was here, the area under the curve of this would be greater than alpha, and I will, because this is just the PDFs here, and this will be my, because this checks the probability of T greater than equal to T observed. I hope this is clear. Shall we quickly revise it once more? Let's do it. So step 1. So what are we doing? We are comparing the mean recovery time of 2 medicines, and we have some data. Step 1. Have the null and, so get your null and alternate hypothesis. We had the null hypothesis that mean recovery time for medicine 1 and medicine 2 both are same. Alternate hypothesis, no, that they are not same, less than or not equal to. Not interested in this. I'm not explaining that now. So I'll go into the details of this later, just after this. So this is the thing which we want to accept or reject. So we have this in place. Now we have to decide what kind of test are we going to use. What kind of test statistic will be there. Okay, what kind of test we are going to use, and depending upon that my test statistic will come. So we decided that we'll go with t-test because my sample size is less than 30. Then we found out what is the test statistic. We saw the T observed, and then we found the test statistic, and we got the distribution. The distribution will be known for the test statistic, and we got that, and we calculated the value for T observed. In the next step, we decided what will be my significance level. So that is 5% is standard. We say kept it 5%. That's my significance level. In the next step, we calculated the P value. P value is the probability of area, probability of seeing any test statistic that is greater than or equal to T observed. So here, this is my T observed, and this is the probability of seeing. So this is a PDF of some test distribution, some T distribution. It can be T distribution, normal distribution, whatever test, chi-square distribution, depending upon the test we will have. Here it is T distribution. Okay. So the T observed area the greater p-value is the area under the curve beyond t observation, t observed. Okay, that is for t which is greater than or equal to t observed. What is the probability? So this is the area under the curve. Here we'll get this value from the table. Okay, what is the value? We can get the corresponding value. Similarly, for this significance level, we get a value that what will be the area under the curve for this t alpha. So we'll have the 5% number. We'll get this t alpha, t value, t alpha. We'll get the t observed from here. We get the t alpha from here. So we can easily compare where my t alpha is. In this case, if we want to compare p values, we can just compare if t alpha. I'll write it in different terms. If t alpha is greater than t observed, or t alpha is less than t observed. Greater than means towards the right. If t alpha was less than this, means it is well beyond, well in the acceptance region, means my t observed is somewhere here. So that's why my t alpha is on the right of it. It is more than this. So I will accept here. I will accept the null hypothesis because it is more than the significance level. It should be at least at this level. So at least 5% or at least 95% of the region should be there in the acceptance and 5% should be in the rejection. So this is my critical value at t alpha. So if my t alpha is greater than this, means I'll accept it. But if my t alpha is less than t observed, which is in this case, it is less than this on the left side of this. So my t observed, the area under the curve will become less than the significance level. The p value will become less than that significance level, and you will reject the null hypothesis, what we did in this case, and we rejected the null hypothesis and accepted the alternate hypothesis that they are not equal. I hope hypothesis testing is clear.